Good evening, and can you see me? Okay, okay. Good evening, I'm Federica Fiorucci from sorry, because non mi risento in cuffia. Faccio così, perché sennò non mi risento in cuffia.
Non c'è problema.
Sorry. Okay, good evening. I'm Federica Fiorucci from from the Institute of Research for Geohydrological Protection of the National Council of Research in Perugia, and I present a data-driven method for assessing the probability for terrain grid cell for initiating rockfalls on a large area. Okay, the location of potential source of rockfall requires expert analysis for the cliff in the study area, which is typical time-consuming and expensive procedure. This makes the identification of potential sources a limiting factor for a systematic rockfall study over large areas. And the common way of selecting source areas is to establish a slope threshold above which any grid cell is a potential rockfall source. In this work, we build a probabilistic model that both locate and assign a probability of failure in an homogeneous way in a very large area. This work was supported by Rete Ferroviaria Italiana and was applied to a territory around the Italian railway managed by Rete Ferroviaria Italiana RFI. Just to give some figures and so an idea of the dimension of the study area, the total length of the railway track is 70,000 kilometers, and the total planimetric area where source area were identified is 25,400 square kilometers. We use a 10-meter shell size grid in Italy. Moreover, we use a slope unit because this portion of territory represents elementary slope with a well-defined boundary, and we are confident that the runout of the simulated rockfalls stay inside this boundary. This is a workflow of the procedure. The procedure comprises three main steps. The first one is the selection of a set of slope units intersecting the railway. The second is the expert mapping of the subset of rockfall source areas within representative slope unit in each topographic unit. And then finally, we use the expert mapping to statistically generalize the source areas to different grid cells. In detail, what we did was identify a 1 kilometer buffer, then select the slope unit intersecting this buffer. The buffer is around the railway network, that is the red line. And expert geomorphology, using expert visual interpretation approach, mapped the rockfall source areas using Google Earth inside the slope units. The expert mapping was done in all of the 29 topographic units, and the expert map produced was used as input to infer the probability of any grid cell to be its source. The probability of each cell to be a source was calculated as follows. We selected the slope units containing the mapped polygon. Then we calculate the histograms of the distribution of the value of slope angle in the cell within the mapped polygon and within the whole slope unit. For each bin of 2 degree width, we took the ratio of the two histograms, the value of the slope within the sources over the value of the slope within the wall slope units. This value range from 0 to 1 for construction, because the number of the cell belonging to source areas following in each bin are less or equal to the number of cells in the same bin for the wall slope unit. And so we have a probability point that are the green dots in the graph. Then we use the value of the histogram ratio, so of the green dots, to build a model P for the probability of a grid cell to be a source. In this graph, we can see in black the histogram average with the black line. With the blue curve is a nonlinear fit of the value estimated from the observed data with the function that is this one. And the red curve is a nonlinear fit of a quantile regression with the 90th percentile with a function containing a single parameter C. We decided to use the quantile regression to assign the probability of a grid cell to represent a source area, because we believe that it maximizes the information extracted from the observed data. Moreover, we use a function with a fixed exponent, the fourth power, because using a parametric exponent, the resulting curve systematically underestimates the probability of source area for large value of the slope. Using the method, we obtain a different function for each topographic unit. In total, we have 26 functions. 3 of the topographic unit was 29, but in 3 there wasn't were without potential sources in the expert mapping, because are in a flat area. And we evaluate the agreement between expert mapped area and statistical generalization using the hit rate. The numerical result of the comparison indicated the agreement is poor in 2 units and could be considered low. It means less than 50% in 4 units. But it's good in the remaining, and for 3 units, the procedure account for the 80% of the mapped source areas. And finally, in this image, is shown a probabilistic map of the potential sources. The probability was used as a proxy for the number of trajectory to be simulated with the software stone. The 0-1 probability corresponds to 0-100 simulated trajectory. So, as you can see here, the probability is transformed in the number of trajectories. Higher probability area are in the dark brown. The comparison with the expert mapping sources show that is the black represented with the black polygon, show a good agreement, and a good agreement is also found if the most likely source area are compared with a huge national landslide inventory IFI for the rockfall type. IFI SIFI does not distinguish source area and the position, but the map the polygon map this feature as a single polygon, and so we selected the higher part of the polygon here. The green one, the higher part of the polygon, using the 90th percentile of elevation to obtain the most probably source location of rockfall. Also in this case, we have a good agreement with the modeled sources. This work is published and wided in a publication where we use the modeled rockfall source area to run the rockfall susceptibility. The paper was published this year. I would like to leave some other key papers to understand the whole work, because there are reference to topographic units, slope units, stone, and so maybe are useful also this publication. Thank you for watching, listening, and getting over the time difference.